Excuse me. Now, we have a new situation where we have maybe the same wheel, but it doesn't matter. Well, we have a wheel of radius 4 meters. We haven't specified a mass. But we have specified that omega is 0 at the pi over 2 position. That is, if we measure everything from the positive x-axis with the x-axis to the right, if we measure all angles counterclockwise from there, the pi over 2 position is here. So the net force, well, so we assume a net force of 1,000 newtons. Unlike in the preceding example, this 1,000 Newton force is always vertically downward. Now that is, for example, the force that you would have if you put 1,000 Newton weight and attached it to the wheel. Okay, now we assume that we give it maybe just a little nudge up here, and it's an ideal situation, so we have no friction. Give it a little bit of a nudge, just the most microscopic nudge, a negligible nudge, but we still move it past the equilibrium position, just an iota, and then it'll start rotating downward in response to the torque produced by this force. So the question then is, what is the angular velocity at the 3 pi over 2 position? That is, when the wheel has come around to here. Okay, again, this vertical downward force, and I don't think I said it, is exerted at a point on the rim. That's kind of implicit in what I said, but let's make it explicit. Okay, some fixed point on the rim. When it's at the pi over 2 point, we give it just a little nudge, and the 1,000 Newton downward force stays there until the wheel is rotated around to here. And presumably, maybe it stays there, maybe it drops off. We don't care what happened beyond that, unless we make some assumptions or have some conditions. Okay, well, so what's omega at the 3 pi over 2 position? And apparently we still have the 3,000 kilogram wheel. I didn't specify that up here. I said we didn't know what the mass was. Well, it turns out to answer this question we have to know what the mass was. So that is what we use. Okay, so there's our situation. Okay, 3,000 Newton rim of the wheel, 3,000 Newton hoop, 1,000 Newtons vertically downward. Start from here from rest. What's the speed by the time we get down here? What's the angular velocity at this point? So to do this, we're going to use the work energy theorem. Okay, so we're going to use the work kinetic energy theorem. Again, this is an ideal situation. There are no dissipative forces, and of course in reality there would be. But if there are no dissipative forces, then the work done by the net force is equal to the change in kinetic energy. So we have to figure out what work is done by this 1,000 Newton force, which in the absence of other forces on a perfectly balanced wheel is going to be the net force. Well, then, in this case, the work done by the net force as we move from here to here is what? Well, we could draw a vector from here to here, and we see that it's parallel to the 1,000 Newton vector, so that the projection of one vector on the other is just the vector itself. So when we multiply them, we're just multiplying the 1,000 Newtons by the 4-meter displacement. They're in the same direction, so you're going to do positive work. Gravity will do positive work on the system. So 1,000 Newtons times 8 meters, that's 8,000 joules. So at the 3 pi over 2 position, the kinetic energy has to be 8,000 joules. Follows that 1/2 mass of the wheel times v squared is 8,000 joules, where v is the speed of a point. Don't know why these words escape me, of a point on the rim. So we set that equal in any case, and we get the speed. Okay, and the calculation's straightforward. We got 2 times 8,000 joules up here, 3,000 kilograms down here. This should be a very familiar calculation by this point in the course. And that gives us about 2.3 meters per second. And it follows then that omega is speed on the rim divided by the radius. Okay, and that's about 0.6 radians per second.